So when scientific models are developed, scientists do a variety of experiments which then culminate and support different models. And we start with the atom. The model we started with was Dalton's model of the atom. And then there's the subatomic particles, and they did more experiments. That was modified, and we got to J.J. Thomson's model, which remember was the plum pudding. And then they did the gold foil experiment, and Rutherford's model came to be more accepted. A modern day, the nuclear atom, where we have the protons in the nucleus and the electrons outside of the nucleus. Remember, it wasn't Rutherford that discovered the neutrons there. But we have this modern atomic nuclear model. But what Rutherford's model didn't do was explain the location of the electrons in relationship to the atoms on the periodic table. So we knew the electrons were outside the nucleus, we knew some of their characteristics, but we didn't have a model that would help us understand what we see in the relationship to the organization of the atoms on the periodic table. So in order to kind of begin to understand the electrons, we have to take a step back and understand just a wee bit about electromagnetic radiation. Now, electromagnetic radiation, which can also be abbreviated EMR, it is one way that energy travels through space. And in this course, we're just kind of gleaning a few of the words that will help us understand a little bit about the electrons. But electromagnetic radiation could be an entire course in and of itself, and really to completely understand the electrons, we would have to investigate it a little bit more. And if you take Chemistry 1, you will begin that a little bit more in-depth investigation of electromagnetic radiation. But for us, we're going to take a few of its characteristics and understand how it relates to what we see and how we can understand the electrons and their location a little bit better. So I already mentioned that electromagnetic radiation is one way that energy travels through space. And what it all does, and let me tell you some of the forms. I have the spectrum in a couple slides, but it's things like X-rays and visible light and gamma rays and ultraviolet light. And so it's these different forms of energy. And one thing they have in common is that they show wave-like behavior. So if you think of the ocean, which also has wave-like behavior, that is how this radiation travels through space. Another thing that these types of the electromagnetic radiation has in common is that in a vacuum, it all travels at the speed of light, which is 3 times 10 to the 8th meters per second. Now, a couple of the basic characteristics of electromagnetic radiation that we look at are wavelength, which is given the symbol of lambda. It's a Greek letter. What I'm saying is lambda. And wavelength is the distance between the consecutive peaks. So a peak is the top, so consecutive would mean one after the other. So if I measured that distance, you see here I get lambda. You could also measure from what's called a trough. That would also be the same distance. So that's the wavelength. We also have frequency, which is the Greek letter nu. And frequency tells you how many waves pass a particular point per second. Then we have the speed, which tells you how fast it's traveling through light. And remember, in a vacuum, all energy travels at the speed of light. So here is the electromagnetic spectrum, and it gives you an idea. So there's this evidence of this wave-like nature, how this energy travels through space like a wave in tiny packets, and we can relate that to the energy of the little packets of light, which we call a photon. And the energy of that photon, E here is energy, is related to, this is a constant. It's named after a person. It's called Planck's constant. We have this frequency on the top here, and then here's lambda. That's the wavelength. Can't write wavelength there. So that is the wavelength of the light. So looking here, we can see that energy is inversely related to wavelength because the wavelength's in the denominator. And what that means is the longer, so a long wavelength means you're going to have a low energy because they're opposite. So the bigger the wavelength gets, the smaller the energy gets. Or you could rephrase it in the other way, and we could say a shorter wavelength would mean we have a high energy. So let's look at our electromagnetic spectrum. So the wavelengths are down here at the bottom, you can see here. And it tells us that it's in meters. So this is 10 to the negative 16, and this over here is 10 to the 6. So this end has a shorter wavelength, so gamma rays, this end, has a higher energy. And this 10 to the 6, these radio waves, these have a lower energy. So the energy of the light relates to its wavelengths. It's also kind of cool if you look at the visible spectrum, you see that different colors of light will have different energy. Now this spectra here is in nanometers, this part of the spectra, but this end, this has shorter wavelengths. So this, the purple light, has higher energy, and then compared to red light, which would have lower energy. So the colors of the light actually can give us insight into the energy of the radiation itself. Now, I don't know if you've ever heard of Roygbiv, but that is a way that I remember. Now, this spectra is written the opposite, but Roy are red, orange, yellow, G, green, blue, indigo, violet. So that is a way, I think of it as a name, that I can remember the color of the rainbow of our visible light spectrum. Red having the lowest energy, going through violet, which has the highest energy. Now, energy, we can treat this with its wave-like behavior, but it also comes out in little packets we call photons. So when we think about light, do we treat it like a wave because it has a wave motion, or do we treat it like a particle because it has these little packets of light called photons? Well, scientists have agreed to use both. It's called wave-particle duality to explore or explain light. That would make the best model if we can use both, and we're going to see that that duality helps us understand what electrons do as well.